Hello students, this is Dr. Anup Sanchela. I hope you will learn active medium, pumping source, and today we will talk regarding the optical resonator. Optical resonator generally consists of two opposing plane mirrors, this and this, with the active material placed in between them. One mirror is semi-transparent and other is made 100% reflecting. This is semi-transparent and this is 100% reflecting. The mirrors are set normal to the optic axis of the materials. And this structure is known as the Fabry-Perot resonator. If we understand this in details, this resonator, or to construct an oscillator which can supply light energy and act as a source of light, one must couple a part of output back into the medium. What does it mean? It means if you want to construct this resonator or the oscillator, the output should be baked into this medium. This can be achieved by placing the active medium between two mirrors which reflect most of the output energy back to the system. Such system of two mirrors represents a resonant cavity. Now to obtain an output beam, one of the mirrors is made partially reflecting. Thus imagine a wave that starts from, from one of the mirrors and travels toward the other in passing through the active medium. It gets amplified. If the second mirror is partially reflecting, if suppose it goes like this and this is partially reflecting, then the wave is partially transmitted and the rest is reflected back towards the first mirror. In traveling to the first mirror, it again gets amplified and returns to the position it has started from. It means the wave can start from this mirror and this is partially reflected, so it is partially transmitted, again it's reflected back to the first mirror and it gets amplified. Thus, in between the two mirrors, we have waves propagating along both the directions. So you can say that this is the oscillator. It can supply the light energy or act as a source. Now we can understand this thing in step by step. Let's think the first stage where the system in the equilibrium condition, the atoms are in the ground state. An active material placed between two mirrors. Now if we supply the energy through pumping. That pumping can done by electrical, optical or chemical. The atoms gets excited from ground state to excited state, and then spontaneous emission, this one, can occur from excited state to ground state. To the metastable state. The metastable state where the atom staying longer time is compared to the excited state. It means in the metastable state the atoms stay about 10 raised to minus 3 seconds as compared to the excited state the atom stay 10 raised to minus 6. It means in the metastable state atom can stay longer. And emitted photons are highly incoherent. In this third stage, photon emitted in a direction other than along the direction of the optical axis or parallel to the optical axis which removed from the system, and photons emitted in a direction along the optical axis can reflected through the 100% reflected mirror or reflected through a partially reflecting mirror. In that path, they also de-excite the other atoms, and the de-excited atoms can create the photons. In this way, number of coherent photons can increase. In the fourth stage, on at the one hand, number of incoherent photon decreases and number of coherent photon increases. This highly coherent photon superimposes multiple times, and slowly optical intensity gets amplified. When the enough intensity will build up, the laser beam will emerge from the opening provided. It means full stimulated emission happens and coherent laser beam can be generated. So that's how the optical resonator works, and it can generate the laser through oscillations, photons back and forth in the active medium through reflecting one partial and one fully mirror, and you will get the coherent monochromatic laser beam. So this is I already covered. Okay, for resonance, it is necessary that when wave returns after one round trip, it should be in phase. It is in phase with the existing wave. For this to happen, the total phase change suffered by the wave in one complete round trip must be an integral multiple of 2 pi. Then only when the waves returns from one round trip, it is in phase with existing wave if the integral multiple is 2 pi. So that the standing waves are formed in the cavity. If d is the represent the length of the cavity, we can write 2 pi upon lambda into 2d is equal to 2m pi, where m is the different oscillation frequency. Lambda is the wavelength of the radiation in the medium enclosed by the cavity. Refractive index is n0 of the medium enclosed by the cavity. So this lambda can be written lambda 0 upon refractive index, and this lambda 0 is nothing but the c divided by mu, frequency, velocity of the light, and the frequency. So this lambda 0, if we put in this equation, and this lambda if we put in this equation, then you can get the frequency equation. Mu is equal to mu m is equal to c upon 2 n0d. If we take the helium neon laser, the refractive index m0 is 1. So that's why mc2d. And this is the different oscillation frequency which can construct the longitudinal modes. You know the longitudinal modes like m is equal to 1. So you know this is, you have learned that the string from means 1 mode, 2 mode, 3 mode, like so different oscillation modes. In the next we will learn the different configuration for optical resonator. So this is the different configuration of the optical resonator and how it can be useful to generate the laser. So first one is plane parallel optical resonator. This arrangement is rarely used in large scale lasers due to difficulty of alignment. A mirror has to be perfectly aligned, or it's aligned parallel with a few seconds of arcs. And this difficulty can be solved by a small mirror separation distance. It's less than 1 centimeter. If we put the separation distance of the mirror is less than 1 centimeter, this difficulty can be solved. And this resonator can be used in microchip, microcavity, and semiconductor laser. Next one is concentric resonator. If the two radii are equal to half the cavity length, concentric resonator can be formed. This type of cavity produces a diffraction limited beam at the center of the cavity. Third one is we will take the hemispherical because it is similar to the concentric. The hemispherical is similar to this is the uh, this one our spherical with one plane mirror and one of the radius equal to the cavity length. And then we will take the confocal resonator or cavity. A common and important design is the confocal resonator with mirrors of equal to the cavity length. This design produces the smallest possible beam diameter at the cavity mirror for given cavity length, and often used in lasers where the purity of the transverse mode pattern is very important. And last one is concave and convex cavity mirror, convex cavity resonator. A concave convex cavity. Here, one convex mirror with negative radius of curvature. This design produces no intra-cavity focus of the beam, no intra-cavity focus of the beam, and thus is very useful in high power lasers where the intensity of the intracavity light might be damaging to the intracavity medium if brought to a focus. So this is how different configuration of the optical resonator. In the next lecture we will learn lasing action and characteristics of lasers and helium neon lasers and ruby lasers, working principles and construction. Thank you.